In this lesson, we're going to look at the relationship between Ka and Kb, and we're also going to be introduced to the common ion effect and then also look at buffers. So to begin with, we're going to first write the acid dissociation reaction for ammonium ion. And so in this case, ammonium is going to serve as the acid, so the reaction would be NH4, and it's going to produce NH3 plus hydrogen ions. Now you could also write this with water to produce hydronium ions. To write the base dissociation of ammonia, NH3 is going to react with water and it's going to produce ammonia and hydroxide. So there's your reaction there. So if I wanted to take these two reactions and add them together to get the overall reaction, what you actually will find is that it ends up being the reaction for the autoionization of water. Here it doesn't show the second water on the reactant side, but if you imagine it, then instead of hydrogen ions, it would be hydronium ions. So that is the autoionization reaction of water, which tells us since we added these two reactions together to get that third reaction, the autoionization of water, when you add two reactions together, you need to multiply their equilibrium constants together, and therefore that tells us that Ka times Kb, which are the equilibrium constants for those two reactions, when you multiply them together, that actually gives you your Kw. So that formula there, Ka times Kb equals Kw, that allows you to relate Ka and Kb. Another important thing to keep in mind, since your Kw is 1 times 10 to the negative 14th, if you take the log of each of these values and simply add them together, so the pKa plus the pKb, that will give you your pKw, which simply equals 14. So that further helps you in relating Ka and Kb to one another. So what we're going to do right now is we're going to see how we can take Ka and actually determine the strengths of acids and bases based on values that are given to you in this example problem. So here it tells you that the Ka of acetic acid is 1.8 times 10 to the negative 5th, and the Ka of hypochlorous acid is 3 times 10 to the negative 8th. Well, based on our basic knowledge of Ka, I know that acetic acid is a stronger acid simply because more of it dissociates, therefore giving it a larger Ka value. Now, what we need to do is calculate the Kb for their conjugate bases. And so all you need to do is take your Ka times your Kb, set that equal to the Kw, and that will enable you to calculate the base dissociation constant. So for the acetate ion, I'm going to take 1.0 times 10 to the negative 14th and divide it by the 1.8 times 10 to the negative 5th. What I end up getting for the Kb is 5.6 times 10 to the negative 10th. If I do the same thing, if I take the Kw, which is 1 times 10 to the negative 14th, and divide it by the Ka of hypochlorous acid, that gives me the Kb of its conjugate base, which is 3.3 times 10 to the negative 7th. Therefore, I know that ClO minus, which is the conjugate base of hypochlorous acid, is a stronger base than the acetate ion. And that actually makes sense because remember, the stronger an acid is, the weaker its conjugate base is. So since acetic acid is stronger than hypochlorous acid, that means that hypochlorous acid's conjugate base would be stronger. So we're able to calculate Ka and Kb. If we know one of them for either an acid or a base, then we can calculate that other value for its either conjugate acid or conjugate base by using the relationship Kw equals Ka times Kb. We're now going to switch gears and look at the common ion effect. And the common ion effect notes that the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So for example, if I have acetic acid and I add to that solution sodium acetate, the common ion being the acetate ion, then the ability of that weak acid, that weak electrolyte, to dissociate is decreased. So let's actually look at an example of that right now. So this here is an example of a common ion effect problem. And you specifically know that because I have my weak acid, my nitrous acid, and I'm adding a salt that has a common ion, the NO2 minus. So as you can see, I'm going to write my dissociation reaction of this acid. So weak acid, so it's going to be double arrow. It's going to produce hydrogen ion and nitrite ion. Okay. I'm going to create my ice chart just like before. In this problem, I start with a concentration of 0.085 molar for my acid, and I have a concentration of 0.10 molar for my nitrite ion. Keep in mind this is your salt, however, we're just concerned with the nitrite ion because this is soluble. And so the way that this is going to change what we've been doing so far, if you notice, the concentration of the hydrogen ion is going to be 0. And so I'm going to subtract X from this and then add X to these two. So what I end up getting is the following. Okay. I know my Ka, it's 4.5 times 10 to the negative fourth, so I'm actually going to solve this right now. Ka equals the concentration of hydrogen ion times the concentration of my nitrite ion. So it's going to be X times the concentration of nitrite ion all over the concentration of my nitrous acid, which is 0.085 minus X. I'm going to assume that the values of X are small enough that they won't affect these two, so I'm going to get rid of them, and now I'm going to solve my equation. So I get the following. 0.10x equals, when I take 4.5 times 10 to the negative fourth times 0.085, I get 3.825 times 10 to the negative fifth. I need to divide both sides by 0.10, and so I end up getting that X equals 3.83 times 10 to the negative fourth molar. It asked me to calculate my pH, though it doesn't ask for my concentration of H+. So to find the pH, I just need to take the negative log of this value right here. And when I do that, I end up with a pH of 3.42. Now, if I didn't have NO2 minus in my initial solution, this is how the problem would look. This is how it would be different. So I have my acid dissociating into its ions. Okay, I have my ice chart again. I start off with only 0.085 molar. I don't have my other two products because this is not a common ion problem. Therefore, I'm going to have minus X plus X plus X. So when I solve this, minus X, this is just going to be X, this is going to be X. So I end up with my Ka, which is 4.5 times 10 to the negative fourth equals X squared divided by 0.085 minus X. Again, I can ignore this X in the denominator, so I'm going to ignore that. So I'm going to take 4.5 times 10 to the negative fourth multiply by 0.085, and I get 3.825 times 10 to the negative fifth. That equals X squared. And so when I square root that, I get that the concentration equals 0.00618 molar. So notice this value here, the concentration of hydrogen ions is higher than that that's produced when you have a common ion. So by having the common ion, that decreases the extent to which the electrolyte can ionize. It can dissociate. Therefore, I end up with less H plus because less of my nitrous acid can dissociate. The next concept that we're going to look at are buffered solutions. And buffered solutions use this concept of the common ion effect, but enable us to consider how solutions can actually minimize the effect of adding a strong base or a strong acid by limiting how much the pH is changed of their solutions. So buffers specifically are solutions that contain a weak conjugate acid-base pair, and they can resist drastic changes in pH when small amounts of strong acid or base are added. Now, they resist change because if, for example, a strong base is added, so hydroxide ion is added, the weak acid, so in this case HF, is able to react with the hydroxide ion in order to produce water and fluoride ion. If you just had hydroxide in solution and it wasn't consumed, then that would severely increase the pH of the solution. But since we can increase the concentration of the fluoride ion, which is a weak base, that limits how much the pH is going to change. In contrast, if I add a strong acid, H+, then the fluoride ion is going to act as a weak base with that strong acid, and it's going to produce hydrofluoric acid, which is a weak acid. Again, it causes the pH to decrease, but only slightly, not as much as if hydrogen ions were allowed to exist in solution by themselves. And the way that we prepare them is by mixing a weak acid or a weak base with a salt of that acid or base. So for example, NH3 would be mixed with NH4Cl, ammonium chloride, because ammonium, that ion, is its conjugate base. So this should bring to mind the concept of the common ion effect, and that's exactly what it is, having a strong electrolyte in solution in conjunction with its either weak base or weak acid. So the Henderson-Hasselbalch equation actually enables us to calculate the pH of a buffered solution. Here it is right here. Notice it's pH equals your pKa plus the log of the concentration of your base divided by your acid. Now, since, as we'll see in our example problems, any change in concentration to the base or acid in order to reach equilibrium is really small to the point at which we ignore it or cross it out, we can actually assume that the initial concentration of the base and the acid in a buffered solution, that is the equilibrium concentration, and therefore we can just plug in those values for the concentration of the base and the acid. Now, a buffer's capacity is the amount of acid or base that the buffer can neutralize before the pH begins to change significantly. And the important thing for you to remember is that the greater the amount of conjugate acid or base, the more resistant it's going to be to change. So in order to calculate the pH of a buffer that has had an acid or a base added to it, what you need to do, let's say for example, a strong acid is added to a buffer. You need to look at the reaction that occurs, so you can see X minus, which is your weak base, reacting with the strong acid to produce HX. You need to calculate the new values for the concentration of your acid, HX, and your weak base. With those new values, you can calculate the pH by using either ice charts or the Henderson-Hasselbalch equation, and I'll show you an example of that in just 1 second. If a strong base is added, then that's going to react with your weak acid, and then you again will need to calculate your new values for your weak acid and your weak base, and then again use ice charts or Henderson-Hasselbalch equation to calculate the new pH. In this problem, it asks you to calculate the pH of a buffer that's composed of 0.12 molar benzoic acid and 0.20 molar sodium benzoate. So I'm actually going to show how to do this 2 different ways. The first one I'm going to show you is using ice charts in order to determine the pH. And then I'm also going to show you the fact that you can actually use the Henderson-Hasselbalch equation. So for this reaction, I'm going to show the dissociation of benzoic acid. The formula for benzoic acid is the following. And this is going to dissociate, it's a weak acid, it's going to dissociate into hydrogen ion plus C7H5O2 minus. Okay? The only information that's not given to you in this problem is the acid dissociation constant, which is 6.3 times 10 to the negative fifth. Okay, so let's solve for the pH of this buffer. I'm going to create my ice chart. I know that the initial concentration for benzoic acid is 0.12 molar. I know that the initial concentration for the benzoate is 0.20 molar. I know the initial concentration of hydrogen ions is 0. So I'm going to lose X, gain X, and gain X for this reaction. So my equilibrium concentrations will be the following. Now I can actually plug this in for my equilibrium expression. So my Ka, which is 6.3 times 10 to the negative fifth, that equals X, my concentration of hydrogen ions, times 0.20 plus X, divided by the concentration of my benzoic acid, which is 0.12 minus X. Again, remember, I'm assuming that this change in X and this change in X are not significant, and therefore when I solve this, I end up with 7.56 times 10 to the negative 6 once I cross-multiply 0.12 by 6.3 times 10 to the negative fifth. I'm going to set that equal to 0.20 times X. Therefore, when I solve for X, I get 3.78 times 10 to the negative fifth molar. Now all I need to do is calculate my pH. So my pH equals the negative log of that value, because that's my concentration of H plus. And so when I calculate that, I end up getting 4.42 for my pH. Now the other way of doing this, I agree that I'm not at equilibrium with this problem, but since we ignored the change in X, so the change in concentration for these two, I can assume that my initial concentration for my acid and its conjugate base are going to be the same as the equilibrium. So the equilibrium concentration and the initial concentration are the same. So I can actually just use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is pH equals pKa plus the log of your concentration of your base divided by the concentration of your acid. So my pKa, the negative log of 6.3 times 10 to the negative fifth, is 4.2 plus, 4.2 plus the log of my concentration of my base divided by my concentration of my acid, and that ratio is actually 1.67. And so when I solve for the pH, I end up with 4.42, which is exactly what I got there. So you can do it either way. I personally prefer to use ice charts. However, obviously the Henderson-Hasselbalch equation is much quicker to solve. In this problem, you have a buffer that's created with acetic acid and sodium acetate, and what it's asking you is to determine the pH of the buffer once you add a strong acid. So before you get started with this problem showing the dissociation of the weak acid, what you should do is figure out, okay, what is hydrochloric acid going to react with, and figuring out how that affects the concentration of your acetic acid and your acetate ion. And so what you should realize is, since this is an acid, it's actually going to react with the acetate ion, which is C2H3O2, and so it's going to react with your strong acid, and it's going to produce acetic acid. So we need to determine stoichiometrically how this affects our concentration of our weak acid and our weak base. So specifically, I know that I start off with 0.3 moles of my acetate ion, and I have 0.020 moles of my strong acid, and then I have 0.300 moles of my weak acid. So in order for all of the hydrogen ion to be consumed, which it must in order for the buffer to be effective, you must use all of this up, which means it's going to consume that amount of your acetate ion, which means it's going to add that much to your acid. Keep in mind, I am remembering the stoichiometry relationships, however, there are no coefficients and therefore it's just all X. So for here, my new concentration of my acetate ion is going to be 0.280 moles. I have no strong acid left, that's the point, and then I have 0.320 moles of my weak acid. Now I can determine the concentration of these guys. So I'm going to divide both of them by the volume of the solution, which was 1.00 liters. So I know that the concentration of my acetate ion is just going to be 0.280 molar after the strong acid was added, and then the concentration of my acetic acid is going to be 0.320 molar. And now I can actually determine the pH of my buffer. So there are two ways that I can solve this problem. I can use an ice chart, or I can simply use the Henderson-Hasselbalch equation. Remember, the Henderson-Hasselbalch equation is pH equals pKa plus the log of the concentration of the base divided by the concentration of the acid. Now there's one key important point that you need to note. What you should notice is the fact that I'm not given my acid dissociation constant, and so as a result what I'm going to have to do is make an assumption, and that assumption is the following. Since buffers are the most effective when the concentration of their conjugate acid and base are the same, before this entire reaction occurred, I should assume that the log of this entire thing, so the log is going to be the log of 1, assuming that it's the most effective buffer. Therefore, this value is 0 because the log of 1 is 0, therefore my pH equals my pKa. And so for here, my pKa will simply be the pH of the buffered solution, so the pKa is going to be 4.74. Then I'm going to add to that the log of the concentration of my base over my acid, so that's going to be 0.280 divided by 0.320, and what I end up getting here is 4.68. If you did this same problem, except you actually used an ice chart, you would get the same value. Now, the second part of this question asks us to determine the pH of a solution if that amount of HCl were added to pure water. Well, in this case, you just have HCl, and so it's going to produce hydrogen ions and chloride ions. Since the concentration is 0.02, I know that the concentration of H plus that's produced is also going to be 0.020 because this is a strong acid, and since it was in 1 liter of water, it's going to be 0.020 molar. Therefore, when I find the pH of this, I find that it's 1.70. So notice how important a buffer is, or how effective it is at reducing the amount that a strong acid can change the pH, because the pH was only changed from 4.74 to 4.68, while here the pH was changed from 7 of pure water all the way down to 1.70. So that shows you the value of a buffer in minimizing the effect a strong acid, or in other examples, a strong base will have in changing the pH of that substance.